So before we understand how methyl benzene behaves differently when it comes to benzene, so we have to understand a phenomena referred as the ortho para directing, ortho para and meta directing group. Ortho para and meta directing groups. Once we understand what exactly is this, then we can go from here. Before I proceed, very quickly, could you just type in on a scale of 1 to 10 how clear is my voice, and if you are able to see me somewhere on the screen? You can. Could you very quickly just make some kind of a... You can. Okay. I think I'll place it here. Okay. So the first thing what we will understand is, so what exactly is ortho para directing groups? So when it comes to ortho para directing groups, uh, these are, first of all, let's understand who these groups are. So the groups are any group which is a R group. Now remember, R group basically represents any alkyl group. So you have to know who are these ortho-para directing groups. You have to know what do they do, what is the effect of their being present on the benzene ring. And I was thinking if it's okay with everyone, we can go non-stop today without a break, so we can probably finish a few minutes early if that's okay with you. Yeah. So any alkyl group. So when I say any alkyl group, for example, I can talk of, let's say, CH3, that's an alkyl group, C2H5, etc. So methyl, ethyl, propyl, all of these are basically alkyl groups. Then we have the OH group. So this also is an ortho para directing group. And then we have the NH2 group. Okay. So the alkyl group, the alcohol group, the NH2 amino group, all of these are considered as the ortho para directing group. Now, ortho para directing group are also called as ring activators. Ring activators. Okay, so in the next page, I will now tell you what exactly do they do? What is the effect of their being present? So let me know when you're ready. These are the three groups of ortho-para directing group which you are supposed to know. So why we have to study this? Because today's main discussion, methyl benzene, methyl, as you understand now, is a R group. So it's an ortho-para directing group. So first of all, we need to know what exactly do they do. So the effect of ring activators. So we call them ring activators. So when it comes to effect of ring activators, so what usually happens, they push electrons into the benzene ring, into the benzene ring, or you could say they push electrons into the pi electron system. Okay, so because of this, so what happens? So due to this, the electron density sorry, just a second. The electron density increases at position 2, 4, and 6. Due to this, the electron density increases. Electron density increases at position 2, 4, 6 on the ring. Yes, Siddharth, what happened? Do you have any doubt? So what that means is, for example, this is the benzene ring. And let's say you have a ring activating group here. So I'm just putting here like A. So A happens to be the ring activator group. Okay, do you want me to go back to page 1? Just type PG1. Is that what you want? PG, page 1? Okay. Oh, well done. I think we are waiting for your friend also, Sonia. Okay, so this was your page 1. These are, I just started off discussion what is called as ring activator group. So ring activator group also called as ortho para directing group. So what these do, they push the electron into the benzene ring. And because they push electron into the benzene ring, so this is position 1, 2, 3, 4, 5, and 6. Now you might remember when I say ortho position, it's position 1, 2, correct? And if you remember para is position 1, 4, okay? So this is ortho and para, as we say. Position 1, 2 is ortho and position 1, 4 is para. So when it comes to ortho, if position 1 and 2 and the position 1 and 6 is like equivalent, I mean, so if I put something here, it's still considered position 2 if I go from this side. So what we have found that the electron density has increased at position 2, 4, 6. So at this point here, at position 2, 4 and position 6, the electron density has increased. So these areas have become rich in electrons. And when I teach you the electrophilic substitution mechanism using these kind of compounds, you will find that the electrophilic attack will happen at position 2, 4, 6. So basically you could predict where the electrophile, which is the positively charged ion, is going to come, because there is high electron rich area in position 2, 4, 6. We don't have to know why this is caused. Okay, that is not a part of our relevant syllabus. So we just have to know any ring activator. It could be OH group, it could be NH2 group, it could be R group. If any one of these three are present on the benzene ring, electron density will increase at position 2, 4, 6, and the next incoming group will come and get attached at that position, and they are called ring activators. They push the electrons into the ring. I'm done. If you have any questions, let me know so far. So I'm done with the ring activators. If you have any questions, please let me know. If you have no questions, could you type NQ so we can move on to our next part. No questions? Everyone is okay? Okay, good. We are only honey, nothing. Now, let's understand the second category of these compounds. So the first category was ortho para directing group. The second category is meta directing group. Meta directing groups. So what is a meta directing group? Meta directing group are also called as ring deactivators. It's called ring deactivators. So they deactivate the ring. So they pull out electrons from the benzene ring. So they do the opposite from benzene ring. So these guys, they do the complete opposite thing. Okay, and the ring deactivators, the examples are the nitro group, okay, and of course there is a carboxylic group, the aldehyde groups, okay, all of these are considered as ring deactivators, and they cause electrons to be pulled out of the benzene ring. Okay, so there the electron density, now because of this, electron density also increases, just like in ring activators. They also will cause electron density to increase, but the positions will be different. Because they pull out the electrons from the benzene ring, the electron density in this case, electron density is found to increase at position 3 and 5. Position 3 and 5. So you might remember when we say meta means position 1 comma 3. So 1 comma 3 is equivalent to 1 comma 5 if you go on the other side. So what that means is, if this is the benzene ring and you have somebody here who is a ring deactivator, so it's going to pull the electrons out. It's going to pull the electrons out the other way. And at position 3 and position 5, this is position 3 and this is position 5, correct? So at position 3, and this is position 2, this is position 4, and that's 6. So position 3 and position 5, electron density. Oh, okay. Thank you, Arina. Good. I was trying to make some setting change in my screen. So, okay. So meta position, if you remember, we discussed it in the beginning of topic 29. So meta means position 1 comma 3. If there are two groups on position 1 3, we called it meta position. Ortho position means 1 and 2. If there are two groups on the ring at position 1 and 2, we say ortho. If there are two groups on benzene ring at position 1 and 4, we call it para. So ortho, meta, para. Ortho is 1 2, meta is 1 3, and para is 1 4. Is that okay? Got it? So this is meta directing group. So now that you know what is ortho, para, and meta directing group, you will be now in a much better position to understand how methyl benzene does its reactions. So if you're ready, let's go to our next page. Everyone is okay? If you're ready, we go to our next page, please. Okay, so when we look at the reactions of methyl benzene, so this is going to be again towards the second part of this lesson, topic 30, and it has all the reactions here, and obviously very very popular in your exams as well. Most of them will come directly as it is. Reactions of methyl benzene. Now, we study reactions of methyl benzene, but that means in the exams, the examiner can change CH3 and put some other alkyl group, and it will all react and behave exactly the same way. It's not going to be different in any way. Okay, so we are talking of reaction of methyl benzene. So whatever you study for this set of equations, remember what can happen in your exams, that instead of CH3, examiner can give you C2H5 ethyl, they can give you C3H7 propyl, or they will give you a fancy R group which you may not have seen, but everything remains the same. Okay, so let's have a look at the first part. This is the chlorination of methyl benzene. Methyl benzene has a common name called toluene, but Cambridge usually does not use that word. They just stick with methyl benzene. So again, the word chlorination is just a general word. It is not to be confused with the name of the reaction mechanism. So whenever the questions come, what is the name of reaction? We expect you to always mention the reaction mechanism. and not the common names. So I would not want you to say chlorination at any given point of time. This is only for the sake of heading. So there are two kind of reactions which can actually happen. Have a look at this one. In presence of ultraviolet. Now, if you react methyl benzene with chlorine in presence of ultraviolet, you have any idea what will happen? Could you mention it in your Zoom chat? Yes, because ultraviolet is mentioned, so the side chain will undergo substitution. So first of all, this has to be very clear. The edge of the ring cannot go because those conditions are not met. So the side chain means CH3 is now considered as the side chain. So this is the side chain. So whoever alkyl group is put, methyl, ethyl, propyl, whatever. So this is the side chain. Now this is now connected to your AS level topic 14 now, where you studied the free radical substitution of alkanes. I hope you remember. Free radical substitution where H of the alkane is replaced by a halogen in the presence of ultraviolet. So the name of this reaction is free radical substitution. So if they ask you what's the name, please do not say chlorination, that will not be accepted. You have to say free radical substitution. So the H of the side chain will be replaced. So now you will get CH2Cl plus you will get HCl, usually called as chloromethyl benzene, but they won't ask you the name. Okay, are you okay with this equation? Please let me know. If you have no questions, could you type NQ? So we'll go to our next page and we'll see if I change the condition, how does this reaction undergo a change? Okay, once again, if anybody who's joined in late, so we started off with ortho para directing group. So ortho para means they activate the ring, they push electrons into the ring, causing electron density increase at position 2, 4, 6. Then we have ring activators, also called meta-directing. They pull the electrons out of the ring, increasing electron density at position 3 and 5. We are discussing methyl benzene, and as you must have guessed it by now, methyl is the R group, and because it is the R group, it is considered as a ring activator. So it's going to push the electrons into the ring. So we are doing chlorination. So first one is done. Now let's have a look at our second one. This time, if I change the condition in presence of AlCl3, now the reaction completely changes. So I'm still doing chlorine. I'm reacting with chlorine, but now I'm using AlCl3. When this happens, the H from ring will be substituted. So this is the story. The H of the ring will be substituted, not from side chain. Not from side chain. So this is a small comment I'm writing so that you may find it useful. So what that means now the question is, which H should I remove? Keep in mind that this is position 1, this is 2, 3, 4, 5 and 6. Would you want to suggest which H will go? What product do you think I will get? You could write the name of the product, or you can at least tell me which carbon number do you think chlorine will go. Type in the Zoom chat, please. Keep in mind that CH3 is a ring activator. Don't forget that. Keep in mind that CH3 is a ring activator. Which carbon number Correct. So either it will go to ortho position or it will go to para position. See, don't forget the keyword or. Ortho position or para position. It means, I hope you understand, you will get two isomers here. Guys, are you clear that you are going to get two isomers and they are considered as positional isomers? So you will get chlorine at the second position. This is the ortho. This is the 2-chloro-methyl benzene. Or you will get isomer. Don't forget, you will get what is called as positional isomer, which means the Cl will come at position 4. So this is now 4-chloro methyl benzene. Plus, of course, you will get your secondary product. Secondary product will be HCl. So that means if they ask you to write an equation, either you can write 2-chloromethylbenzene or 4-chloromethylbenzene and put HCl as your secondary product. Have you understood? If they give you only one box and they say draw the structure of the organic product formed, you are allowed to draw 2-chloro or 4-chloro. Have everyone understood? If you're okay, um, if you can tell me if you have any questions. If you have no questions, let me know so we can go to our next page. So this was the reaction of benzene with chlorine. On a similar scale, we will now do the reaction of, sorry, methyl benzene with chlorine. On a similar note, we will now do reaction of methyl benzene with bromine. And there is going to be a very important, which part, Siddharth? So what I'm saying is, when you do reaction of methyl benzene with chlorine, you will get two isomers. So in the exams, you are allowed to write any one. So either you can say 2-chloromethylbenzene plus HCl or 4-chloromethylbenzene with HCl. If they give you one box and ask you to draw the structure, you are allowed to draw any one of them. You don't have to make both. Only if the examiner says what are the possible isomers you will get, only then, which I have not seen, only then you will make both of them. Is that clear? If it is clear, we can go to our next page. So now let's have a look at the reaction of, we started off with chlorination of the methyl benzene. So on a similar note, uh, sorry, I did not tell you the name of the mechanism of this reaction. Very, very important point I missed. So the name of the reaction mechanism, name of reaction mechanism is actually electrophilic substitution. We discussed electrophilic substitution in our previous week class when we did reaction of benzene with chlorine and bromine, correct? We also did Friedel-Crafts alkylation and Friedel-Crafts acylation, and I think we did mechanism for everybody. So anytime H of the ring gets replaced, it is always considered as electrophilic substitution. So this is electrophilic substitution. I'm just writing it here. Okay. Now let's have a look at our bromination. Remember, bromination is just a common word, common name. You're not supposed to write that in the exam. Bromination of methyl benzene. It is just to give you an indication that I'm reacting methyl benzene with bromine. Now there is going to be a very important small little point which you have to keep in mind, which actually will be tested later when we do phenols and amines. So just please keep a lookout for this. So when you do the reaction of methyl benzene, okay, once again, don't forget, let me just make that note. The chlorine here is in gaseous form. Okay. But anyway, state symbols will not be, but particularly for the free radical substitution, I just wanted to mention the physical states there. Now, when it comes to methyl benzene, If you want to do a free radical substitution, you can go with UV and then you can put bromine in gaseous state. Now, please be a little careful here. So, as expected, side chain will be substituted and you will get this. So, I don't think any one of you have any problem here. Okay. So, this is the situation A. But if the same reaction is carried out for electrophilic substitution, now you need bromine liquid state. Now this is going to be very crucial later. You please make sure you do not forget this. This is very, very important. Okay, so bromine liquid. Later on, you will be using bromine aqueous in phenol cases and aminobenzene cases, and we'll have to figure out why that's happening. So now catalyst still remains the same. We need AlCl3. Okay, and then just go ahead and would you want to, this is still electrophilic substitution. Could you predict what products you will get? Please predict what products you will get. AlBr3, yes. Could you predict what products you will get? AlBr3, yeah, yeah. Okay, so what will you get? So CH3 is ring activator, which means I will get both the isomers. So I should be getting 2-bromo methyl benzene, or I will get 4-bromo methyl benzene. Plus, of course, I will get HBr, hydrogen bromide. So 2-bromo methyl benzene. Okay, guys, I'm waiting for your questions. 4-bromo methyl benzene. Anybody has any questions? Anyone has any questions? Okay, so just be a little careful. Methyl benzene and benzene, both the reactions, we need bromine liquid. Okay, if you're ready, please make sure the bromine liquid is also there with your benzene structure also. Everyone is fine. Nobody has a problem. Okay. Now, can we try to do the mechanism of this reaction, or so let's do the mechanism of this reaction. So we're going to do some reactions and we'll do the mechanism straight away. Mechanism of chlorination of methyl benzene. I have seen some students struggling here because the curly arrows, the way many students place is sometimes is not correct. I will give you the question, I'll give you a couple of minutes to work on and let me know when you're done and then let's see how. It's exactly the same mechanism what you've done before. Okay, so the first obviously I need you to do is the formation of electrophile. Remember, these are independent questions which usually comes. So could you go ahead and give me the equation for formation of electrophile, which is Br plus. Okay, let me know when you finished. First, you're going to do that, and then we will do the mechanism. So I'm giving you all the outlines. So that's the methyl benzene, and I want you to convert this into this. Keep in mind that I want the Br to come here at position 4. Now that's the only small little challenge. You have to just make sure where the curly arrow should be, how it should be. First of all, let me know if you have finished formation of Br plus. That's the reaction between AlBr3 plus Br2. It will form AlBr4 negative plus Br plus. This is the equation for the formation of electrophile. Okay. Let me know if you're finished. Very good. You've already finished. So if you're going to react this with Br plus, it's just the curly arrow's position has to be perfectly correct. Rest everything should be fine. So I know that Br has to be placed at this position. So the curly arrow must go like this. That's the only little precaution you have to take. Plus there is also one more precaution. The reaction intermediate that you draw, accordingly, you have to show how the pi electron system is broken and how it is redistributed. So the pi electron system will be redistributed like this. This particular carbon will be empty. I mean, it won't be in the pi electron system. I can put H here, I can put Br here. Don't forget the plus sign. This is what the reaction intermediate should look like. And then don't forget there is one more curly arrow which is coming in. So the curly arrow is from this to this. So it loses its electron. The H comes out as an H plus. So that's the H plus which is coming out, which then combines with the Br minus to form the HBr, and the AlBr3 is reformed, because don't forget a catalyst has to be regenerated. And then the pi electron system gets restored. Oh, sorry, it's already done. Okay. I'm waiting for anyone to have any doubts, any questions. This is basically how we do the mechanism. Guys, if anyone has any questions, please. Is everyone comfortable? Same thing will be for chlorination of, okay, I said chlorination, but I did bromination. I'm a bit distracted today. Mechanism of bromination, sorry. Okay. Anyone has any doubts? Nothing? Same thing will be for chlorination reaction as well. Everyone is okay? Okay, so now let's move on to our next reaction, which is nitration. Now remember, nitration of benzene, you got nitrobenzene last time. Do you remember the conditions for nitration of benzene? What was the conditions for nitration of benzene? Do you remember? We use concentrate HNO3, concentrate H2SO4, and what was the temperature? 25 to 60 degrees Celsius. Correct? Okay. 25, hold on. 25 to 60 degrees. Okay. Now, Siddharth, 60, make it 60. So the reagent condition still remains the same. There is no difference. Reagent plus conditions. Again, these are all very, very important questions which keeps coming in the exams. So I need concentrate HNO3 plus I need concentrate H2SO4, and I need 25 degrees Celsius to 60 degrees Celsius. So these are the conditions, reagent conditions for, even for methyl benzene, everything remains the same. Okay, so let's have a look at, first of all, the reaction. Would you want to go ahead and try this reaction yourself? because you have a fair idea now how this is going to go. So why don't you try it? Or you could predict the products. You're reacting this with concentrate HNO3. So I have here concentrate H2SO4, and then I have here, I'm just writing it here so just to so that is you can memorize easily. The NO2 plus obviously is going to come from HNO3. Okay, could you predict the products? Once again, the same situation. CH3 is a ring activator, so which means you are going to get two isomers. Electron density has to increase at position 2, 4, and 6. Position 1, 2 is equivalent to position 1, 6 because if you go from the other side, that will automatically become position 1, 2. So that's why we say ortho. Ortho is position 1, 2, which is equivalent to 1, 6 on the other side. And position 1, 4 is para. So ortho para, as we say. So we are going to get two products here, two isomers. So I will get here 2 nitromethyl benzene, or okay, those who finish, can you please start working on the mechanism of this reaction? I will get here 4 nitro plus of course I will get water secondary product. Normally they will just ask you to predict the product. So 2 nitro methyl benzene, and this is 4 nitro methyl benzene. Okay, go ahead and try to complete the mechanism of this. I want you to develop the mechanism to form 2 nitromethyl benzene. You develop the mechanism to change methyl benzene into 2 nitromethyl benzene. Don't forget, you will be expected to show the formation of electrophile. Formation of electrophile, which is NO2 plus. So in case I'm sure you might remember the reaction what we did in the previous session, formation of electrophile. Very good, well done, Jude. So you might remember I had here the concentrate H, and you can use state symbols as liquid also. Concentrate it is. So concentrate HNO3 liquid reacting with concentrate H2SO4, and you will get here the NO2 plus. Ions will be in aqueous form, plus H2O liquid. We had this update, and then I also have the HSO4 negative. Once again, could you just confirm if the equation is balanced? I think it is. Hydrogen 3, yes. Okay, it's all balanced. So that's the NO2 plus there. So now if you can just go ahead and do the mechanism, please. Please type done when you finish. Some of you already finished, well done. I'm waiting for you to finish. Please type done once you finish. Very good. If anybody needs help, don't hesitate, just talk to me. So I have here, fantastic. Okay, so everyone looks to be very comfortable, good. So that's the methyl benzene, and I need the NO2 plus. I want the NO2 plus to come near the second position, so my curly arrow has to be preferably close to the second position. Okay, and that's about it. And then don't forget, when I break up the pi electron system, I have the H, I have the NO2, so my So that carbon here has to be the one which is outside the pi electron system, and then I have to make a curly arrow inward, and okay. Any questions at this point of time? Guys, any questions? Easy? Absolutely no problem at all. Very good. Okay, so if you're ready, let's go. Now, just a bunch of equation. There's nothing new, but maybe I can give you one small question just now. What came to in my mind based on what we are discussing, just to wake you up a bit. So let's have a look at a very nice question there. So let's say I want you to change this. These are the kind of questions you should expect in the synthesis chapter, organic synthesis, where the examiners gives you a flow chart and you have to work out things. So let's say I want you to change this into, let's say that it's just a small little thing based on, it's a revision opportunity as well. And then I want you to change this into, let's say, okay, see, this is how the questions usually will go. So, for example, I mean, of course, I can change this to CL there. Okay, go. Just complete this reagent conditions for me. So, this is the first stage, the second stage. It is just for revision. It is just for revision. This is typically how paper 4 questions you will get in the exams. They'll ask you reagent conditions, and slowly, as I do more equations, they make more bigger webs than this. That's all. That's how organic synthesis questions come. Okay, so the question is, write, tell me when you're done. Reagent and condition. This is just a small revision, guys. Okay, revision and conditions for 1 and 2. Of course, I can add up more. I can convert this into from here to 2 nitro. So this is just a revision opportunity. So there you go. Some revision opportunity there for you. Let me know when you're done. Oh, did I teach you oxidation? I don't think I taught you that. Sorry. It's going to come now. Sorry, my bad. Okay, let me know when you're done. So what's the first one for? Reagent conditions. So you want to put the CH3 on the benzene ring. So this is based on your previous class. So this reaction, of course, commonly called as the alkylation, sometimes called Friedel-Crafts alkylation. But remember, examiner is always looking for the name of reaction mechanism. So always try to quote the name of reaction mechanism. Please type done when you finish. Reagent condition for the first one and reagent condition for the second one. A reagent condition and the name. Reagent condition and name of reaction mechanism. Please type done when you finish. So for the first one, now please check your answer. So the reagent should be, you can take CH3Cl, CH3Br, CH3I, you can take alcohol, CH3OH. And what was the condition? AlCl3 plus heat. Don't forget the heat. What was the name of the reaction? It was electrophilic substitution. Is everything okay? Everyone got it right? Very good. And for the second one, what was the reagent for the second one? You want to put the chlorine on the benzene ring, so you obviously need chlorine. They won't bother with the state symbols with respect to that, but particularly be careful with the bromine thing. And condition, chlorine will be in gaseous form only. AlCl3, just AlCl3 is enough. Okay. What was the name of this reaction? This is also called electrophilic substitution. Anyone has any questions? Could you type, if you have no questions, could you please type NQ? Now, when you do reactions for methyl benzene, you actually see that it comes off as a revision for reactions of benzene because they're kind of same, but the only difference now that because there is a CH3 group, a ring activator, you could predict where the second group is going, which means I don't think I have to teach you much in the next subheading, which you probably already know. So let's do the alkylation or Friedel-Crafts alkylation reaction of methyl benzene, which obviously is going to be parallel to the benzene reaction that you have studied. Okay, so only small thing to keep in mind is the presence of CH3 and what effect does it do. So Friedel-Crafts alkylation. So what is that for? This is to introduce the R group, to introduce the R group. Now that means your reagent, as expected, reagent will be, it can be Rx or ROH, and of course the condition would be you would require AlCl3 plus heat as usual, and the name of the reaction still remains electrophilic substitution. So we're going a little fast here because these are not new things for you. You already are familiar with it, which means I think you can do the reaction first and then you can do the mechanism also yourself. I don't think you need my help. So let's have a look at the reaction. Okay, so why don't you go ahead and complete the equation? I want you to start from here and I want you to come to, of course, you know what's going to happen, right? So you will again get two isomers. So I'm reacting this with CH3Cl in the presence of AlCl3 and heat, and I'm waiting for you to tell me if you have done this reaction. Type the N for done if you're finished. So we are now introducing another CH3 group into the benzene ring. Very good. So Jude is already finished. She loves the organic. Talal also finished. Well done. So when you're done, very good. So which means once again the same drama that I'm going to get two isomers because the electron density is increasing at position 2 and position 4, which means I will get a CH3 at that position, or I will get another CH3 at position number 4, plus of course I will get HCl. So this is 1, 2 dimethyl benzene. For your entrance exam, I'm not sure, but it probably is called xylene. You can check that later. That's position 1, 4 dimethyl benzene. Okay, nice and easy. So why don't you do one thing? Why don't you develop the mechanism to convert methyl benzene into 1, 4 dimethyl benzene? Go ahead, start work on that. I want you to construct all the mechanism. You already know, you can actually finish in 2 minutes. Mechanism of converting methyl benzene into 1, 4 dimethyl benzene. Anybody wants me to go back to any previous page, please let me know. So I want you to develop this mechanism. Formation of electrophile, you already know how it's done. Oh, okay. Guys are on fire today. Well done. So nice to see everyone's finishing fast. Well done, guys. So I have here CH3Cl plus AlCl3, which will give me AlCl4 negative plus CH3 positive. That's my electrophile. So don't forget, you need to be very clear as how do you make the electrophile. Yes, definitely. Just write PG and 11. Okay, so there's no need to write a comment. Just write PG 11 or page 8, or that's enough. I'll go back immediately to that page. Is that okay? Can I go back on page 12 now? Okay. So that's the formation of the electrophile and the reaction mechanism. So as I said, I want you to start with methyl benzene, and I want you to reach to 1,4 dimethyl benzene. So the curly arrow, well, okay. I can probably put CS3 down and bring the curly arrow this way as well. Okay. And then I have, then don't forget one curly arrow going this way. And then I have an H plus coming out here. Is that okay? Sometimes on a rare occasion, if you find the examiner, they might even put like CS3 plus like this. Okay, so in that situation also, you can just put the curly arrow. So you can decide how you want to switch the curly arrow's position. Okay, so even if it's down or whatever. Okay, anyone has any questions so far? Everyone is okay. So we are okay with the Friedel-Crafts alkylation of methyl benzene. On a similar note, I'm sure you are well aware of the Friedel-Crafts acylation reaction of the benzene. So you can use that information now to do a Friedel-Crafts acylation reaction of methyl benzene. We are almost coming to the end of this lesson. Let me know if you're ready. We'll go to our next page. Everyone is good? No questions at this point of time. Okay, so what we are doing now is we are discussing the Friedel-Crafts acylation reaction of methyl benzene. Now, this is a good revision opportunity. You must first try to remember. So, what happens in Friedel-Crafts acylation? So, when it comes to Friedel-Crafts acylation, this is to introduce Do you remember what goes onto the benzene ring? When it comes to Friedel-Crafts alkylation, you learn that R group goes into the benzene ring. So what happens in acylation? What group goes in the benzene ring? You have to use your benzene knowledge to introduce the RCO, the carbonyl group. Yes, to introduce the RCO group in benzene ring. So that's the story. Okay. So who was the reagent? Who was the reagent? Like the best reagent who can give me the RCOCl. Do you remember? You have done this in benzene. This is nothing new for you. This is the acyl chlorides. You remember? They are called acyl chlorides. Acyl chlorides, they are named as alkanoyl chloride. This is the naming. Alkanoyl chloride. Like ethanoyl chloride, propanoyl chloride. Okay. What was the condition? Anyone remembers the condition? Type in the Zoom chat. It's a revision opportunity. You guys forgot? We did this for benzene also, no? The catalyst and the condition. Anyone? I'm sure you know. AlCl3 plus heat. Alkylation and acylation both requires heat. AlCl3, same catalyst used for both. Okay, so let's do a reaction and then we will do the mechanism. Almost getting done. So let me know if I can go to my next page. This is a very easy lesson, and the good thing is, since the questions will be tested directly, so it's pretty easy for kids to score a lot of marks in here. And quite a bit of, obviously, as you must have noticed, is memorizing, which I think you have already done, so that's a good job there. So let's do some reaction. I'm sure you can complete the reaction. You don't have to copy from the screen. So I'm giving you methyl benzene. Go ahead, finish this equation. And I want to introduce, okay, I want you to change this into, of course, we are going to get two isomers, right? So this is one isomer. I'm drawing one isomer. So I wanted to change this and you will get here COCH3. I'm just writing the display formula so that you know how the connection is being cut. It's a COCH3. Okay, so normally we just write, you'll find always in the books, this is COCH3 written. Okay, so just wanted to open up the structure there for you. Okay, so what do I need to get COCH3? I need COCH3, so I need an acyl chloride who can give me COCH3. So which means I need CH3COCl. See, this is what I need, CH3CO. And this is ethanoyl chloride. I'm going to give you some other practice questions after this. And then, of course, I need my AlCl3 and I need heat. Now, don't forget, I'm going to get two isomers. And the reason why we always end up getting two isomers because CH3 is a ring activating group. So I will get that, or I will get here. Once again, this is just to give you a little idea of how the group is attached. The COCH3 comes in here. Of course, this is the HCl. Okay. Normally, this can be written as in a condensed form. You just have to get familiar with it. Okay, so you can just write this as COCH3 also. It's fine. Okay, is everything okay here? Give me yes or no if everything is okay. Can I give you another reaction for practice? Because many times in the exams, examiner will use SKF to put a little bit of pressure on you. Let me know when you're ready. Type R for ready in the Zoom chat. Everyone is ready? You just let me know. Okay, for example, question comes like this. Okay, I'm waiting for you to finish this reaction. Draw the structure of the product form. Obviously, you have to use the same format which I have used. Tell me when you're done. So the moment you see this, so you know who this is, right? You don't have to worry about the naming, but in case you're interested to know the name, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4. So there is a methyl at the third position. So this is 3-methyl butane oil chloride. Okay, type, and of course, as you notice here, this is ethyl on the benzene. So this is ethyl benzene. So the point that I was trying to make throughout the lesson, whatever happens to methyl benzene, same drama will happen to ethyl benzene. There is no difference. Please let me know if you have got the equation done. Type DN for done. If you think you have the structure of the final product, I'm not asking you to name the compound. Just type DN for done if you think you have the final structure. So, okay. One student already finished. Waiting for everybody. So what you must understand is that this Cl has to will be kicked out. The Cl will be kicked out, right? And then you have to also keep in mind that you have to like swap this like this. Like when you connect it on the ring, you literally have to flip the from here. You have to connect carbon number 1 on the ring. You have to connect carbon number 1 on the ring. Connect carbon number 1 to the ring. So this is a note for everyone. So just make sure that your structure comes correctly. Let me know if you have the correct answer. I still have. Okay, keep trying. I'll wait. Of course, you will get 2 isomers. Don't forget in the exams you're allowed to make only one. But if you can make both, very, very good. I just want to be sure that I have only one student who has sent me the update that done. I don't know. I hope my chat is working fine. Guys, do you need any help? Okay, so another. So I will finish. Okay. Now I'm getting some responses. Okay, so let's check. So I obviously have this, and then I need to connect that to position two, right? So I have here. So just connect it here. Now this the double bond stays, and then I have one, two, three. So one, two, three. Is that what you got? One, two, three, four. Is this what you got? Could you give me Y for yes? Perfect. Okay. What's the alternative? You have to use the SKF format only, no? That's the thing. So it's just a little bit of skill drawing. So I know I need to connect the O double bond. So what you can do is, I mean, you can give it a bit of an angle there. And then what else? And then I can do something like this. Okay, will this work? Guys, give me yes or no if this is okay. Is this structure okay? Okay. Plus, of course, the HCl. Was everyone okay with this question? So you understand sometimes what examiners do. They look at the same idea. They just try to give you put some pressure on you by giving some SKF into it, and that's about it. Okay, everyone is okay. So we have done alkylation, we have done acylation, and we also know sometimes examiners what they can do. They can just put some pressure on you with the acylation, or similarly alkylation also. Even for alkylation also, I can put a fancy R, and this question can come. Would you like to have one more question for alkylation just for the sake of practice? Okay, but these are very typically paper 4 questions, exam questions that you will be facing. So for example, they will give you something like this. Okay, so which obviously this means there is an R group here. And if I'm going to react this with this, can you complete this equation? This is just for practice, that's all. This is all electrophilic substitution going on. Good to know that this is all electrophilic substitution going on. Anything that comes on the ring is basically electrophilic substitution. Okay, go ahead. Try to finish this last one for me. This obviously is methyl benzene. This is not to be considered as a phenyl group because I know many people will think, oh, that's an empty bond. So I just mentioned clearly that that's a methyl group there. Or just to be on the safe side, I'm just going to write CH3 because it kind of looks like phenyl, so I don't want any confusion. Okay, so go ahead and complete this equation for me. This is definitely an alkylation reaction going on. This is Friedel-Crafts alkylation because I'm putting the R group. I'm sorry. And this is the acylation going on. Just to see the difference. This is acylation going on because the RCO is coming, and this is the alkylation going on. Let me know when you're done. Cl will be kicked out. Remember, this is carbon number 1, carbon 2, carbon 3, and carbon 4. This is 3-methyl 1-chlorobutane. This is 3-methyl, sorry, 1-chloro 3-methyl. Chloro has to come. Alphabetical sequence, chloro has to come first. So this is 1-chloro 3-methyl butane. So now what you see, your R group has got some other groups into it. So it cannot be only like CH3Cl or C2H5Cl. Sometimes they complicate the R. They put some other stuff into it. Okay, so all you have to do is you know that Cl is going to go, that Cl is going to go. And if that Cl is going to go, this entire thing has to be then connected into the carbon chain. That's the only thing, what skill that you have to develop. So let me know if everyone is comfortable now. So I have here like this, and I know that carbon number one, so don't forget, this is just a little extra hint for you. Connect carbon 1 to the ring. I hope this is being useful for you. You connect the carbon 1 for the ring. So which means I'm going to connect this carbon here, 1, 2, 3, 4. So that's 1, 2, 3, 4, and I have methyl at this position. Is that what you got? Guys, could you confirm? Because if you look, that's carbon number 1, that's carbon number 2, carbon number 3, carbon number 4, that's 3 methyl. That's the R group which is put there. And of course, I can put my second alternative. Okay, help me out with the second one. What do you think? So I have here, so I can put one, two, no, yeah, three, 1, 2, 3, 4, and at the second position, that's a group there. I can design any way I want as long as it's very clear that that's carbon number 1, that's carbon number 2, carbon number 3, carbon number 4, and carbon number 2 has a methyl group there. Okay, is everyone comfortable and how these questions may come? And if everyone is okay, so let's look at, so we have done with all the electrophilic substitution. We know how it works with benzene, we know how it works with methyl benzene. We did nitration, chlorination, bromination, we did formation of electrophils, we did everything. We did a few examples of how SKF questions formats can be used to push the Friedel-Crafts alkylation and acylation questions. Do you have any questions at this point of time? Any questions at this point of time? Everyone is okay? So we are left with, I think, the last of the discussion, that is the oxidation of methyl benzene. Apart from that, I think we covered everything in the curriculum. So let's have a look at oxidation of methyl benzene, very popular area. And once again, whatever happens, why did you put the second carbon? Oh, hold on. Because the CH3 is R group is ring activator, so I can put it on the second carbon or on the fourth carbon. Is that what you're saying? Methyl group on the second carbon. Oh, sorry. Yeah, you're right. My methyl group should not be on the second carbon. Thank you so much. My methyl group is supposed to be on the third carbon. Thank you so much. That's the thank you. That's the third position. Is that okay now? Yeah, thank you. Fantastic. Okay, so let's have a look at the last of the reactions. Again, pretty important, pretty repeated in the examinations. Oxidation of methyl benzene. Of course, we do oxidation of methyl benzene, but any R group on the benzene ring will get oxidized exactly in the same way to form the same product. So it doesn't not even matter how how many carbons are. But let's have a look. Oxidation of methyl benzene. So the reagent that I need is alkaline KMnO4 plus heat followed by dilute H2SO4 aqueous. Okay, so let me know when you're ready. Everyone's ready? So that's my reagent, and we are doing an oxidation reaction. So now I will of course teach you the steps, kind of like the whole thing can happen in two steps. But sometimes if the exam questions comes a bit differently, I'll tell you how to work that out. So what happens is this is your methyl benzene. It's a very simple reaction, and we are doing the oxidation reaction. So when you do the oxidation reaction of methyl benzene, but I'm using alkaline KMnO4. Alkaline KMnO4 means I have KMnO4 with NaOH aqueous, usually NaOH aqueous, or it could be KOH aqueous. So alkaline KMnO4 usually means that we need a strong alkali. So anytime you see this, you can be very, very sure that most probably it is having NaOH aqueous. Okay. And then I also need heat. So what happens now is, see, removal of hydrogen is also called oxidation. Adding oxygen is also called oxidation. So all the hydrogens here will be kicked out. And what you get is the carboxylate salt. We call this carboxylate salt. So we will get here COONA because I am using NaOH. If I was using KOH, I will get COOK. So even if you write COO negative, that also is fine. So this is sodium benzoate. So you see, it's like a sodium salt of the carboxylic acid. Let me write all everything. So this is sodium benzoate. Benzoate. Oh, it's like a carboxylate. This is good for you to know. This is carboxylate salt. So this is the concept. A carboxylic salt is being formed. So and the reason why you should not get surprised, because obviously there is NaOH. You cannot get carboxylic acid. How will you get acid when there is NaOH there, right? Because NaOH is going to deprotonate that acid. As acid is going to lose the H plus, and the Na will come and take its place. So you'll always get COONA. You cannot get COOH at this point of time. Once you have the salt, which is highly soluble, so you want this to happen because you want a lot of ionization to happen. And once you have this, and then you add dilute H2SO4. This step is basically what you're doing is, this is called protonation. I mean, if you want to understand. So we are actually, sorry, more, that's a bit respect to amino acids later. So sometimes we call it acidification. Okay, we are doing acidification. We are just pumping a lot of H plus ions into it. So what it does, it pushes a lot of H plus ions into it. Okay, it's going to put a lot of H plus ions into it, and this Na is going to be kicked out as the Na plus. Of course, the Na plus is going to combine with the sulfate to form sodium sulfate, but that is not our intention. That is not our main focus. Our main focus is that this sodium ion has to be replaced with H plus ion. So that's why we're doing it in like two different stages. So this acidification steps ensures the formation of finally the carboxylic acid. This now becomes benzoic acid. Okay, so what you see now is the methyl benzene gets first changed to COONA, the CS3 changes to CONA, and then it changes to COH in two stages. Okay, I'll tell you how sometimes some questions may be framed. Based on that, you may have to slightly change your presentation of your answer. Okay, I'll give you a few moments to copy down what you need. Just a small little heads up. if 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 your examiner says, okay, let's change this to this in one go, so then your reagent conditions will be alkaline KMnO4 plus heat followed by, like this is for organic synthesis, followed by, suppose they don't give you space, or they don't give you like one extra box, they only give you methyl benzene and directly one box. Okay, so which means that you have to like do you don't have to show the inside sodium benzoate story. So then you go directly from alkaline from methyl benzene, you go directly to benzoic acid. So just be careful how the question is framed. If they don't tell you, you obviously must write this way. But if they give you only one box, which means there is no place for you to draw this, or sometimes they will say, what's the reaction intermediate? I've seen that also. They will give you methyl benzene and then they will say, okay, fill up the reaction intermediate, and then they say, what's the final product? So if they give you like that, that means they're expecting you to do everything. Okay, so I'm done waiting for your questions if you have. Most probably, what you will get is they will give you a box. This is the reaction intermediate, and then they will say organic synthesis usually will have that. So it's always good to know everything. So let me know if you have any questions, please. And interestingly, even if it's not mentioned in the curriculum, but if I do oxidation of ethyl benzene, I will still get benzoic acid. The rest of the extra carbons are knocked off as CO2. But we have methyl benzene in your curriculum, so that's about it. Please let me know if you have any more questions. You don't have oxidation mechanism. And basically, that's the end of topic 31. The next chapter, topic 32, is a very small chapter which can actually finish in 15-20 minutes maximum. So I think let's finish topic 31 also today, and then we can wind up the session. Let me know if that's okay with you. Next lesson, topic 31, is halogen compounds. It's a very small chapter and it will finish very, very quickly. If that's okay with you guys, let's finish one more lesson. Is that okay? Give me a yes or no. Page 16. I'm sorry. I just saw it. And page 15 as well. Okay. Anybody else wants to go back to any previous page? Done? Let me know if you're finished. No questions from this chapter, topic 30. How did you find this lesson? On a scale of 1 to 10. 10 means, okay, everything is easy to learn, no problems. 1 is very, very difficult. What do you think about this lesson? It's a good lesson to score a lot of marks actually. And the good thing about this chapter, the questions also, if you look at the exam questions, they're pretty much like straightforward, the same thing. Not much reagent conditions to learn. Everything is very similar. Curly arrows, you know what to do. And a few, only 4, 5 main equations. Focus on the formation of electrophiles and everything. So it's a good lesson to score a lot of marks there. Okay. I hope everyone is done. So let's finish one more lesson. It's a very small lesson and it talks about halogen compounds. There's only one point which I have to discuss to finish that lesson. So that's why I said let's finish one more lesson today. So this is topic number 31, halogen compounds. This is not halogen compounds for the AS level. This is for A level, and we are only discussing actually haloarine. There's one point what we have to discuss here. So the point that we have to discuss is ease ease of hydrolysis. And this is the first of the comparison situation. There are about 4-5 comparison in your syllabus, I think. And out of these 4-5 comparison, one of them is like an assured question for you. So you need to be very careful wherever there is a comparison going on for anything, acidity comparison, hydrolysis comparison, basicity comparison, any of these three situations will come up with different questions, different compounds I'll give you. Please take a special note to make sure that you learn up all the main key points and the statements there. We are now comparing ease of hydrolysis between CH3CH2Cl and C6H5Cl. That's it. That's the only thing what we're going to talk about in this lesson. And with that, this chapter will finish. Now, I always insist, whenever I teach comparison to the questions, okay, the syllabus might say, oh, the kids must know this as chloroethane. But what I tell the kids is, okay, by the way, hydrolysis basically means I need to knock out the Cl and bring the OH, okay? So what I tell the students is, okay, don't learn it as chloroethane. I want you to learn this as Cl on side chain. Why am I asking you to do it? Because in the exam, they will give you something very fancy. For example, if I give you something like this, do you think this compound which I just now drew will have a similar situation to chloroethane? Give me yes or no. Do you think it will have a similar situation to chloroethane? Is this also chlorine on the side chain? You see this? This is a CH2. You look at that. Which means whatever I will teach you for chloroethane is applicable for any crazy fancy compound what the examiner will give you. Your focus should remain, where is the chlorine attached? If the chlorine is on the side chain, all the key points statements which I'm writing is applicable. Rest is all mango tree here. You just have to copy and paste. That's just the R group for you. Okay, so this is very important. Now, when I give you this is supposed to be C6H5Cl, which you know as chlorobenzene. But I don't want you to learn my comments only for chlorobenzene. This, as you see very clearly, is Cl on the ring. First of all, do you see the difference? This is Cl on the ring. This is Cl on the side chain. Guys, give me yes or no. Do you see the difference between the two, first of all? Please give me yes or no. That's a Cl on the ring, which means if I give you something like this, sorry, if I give you something like this, do you think this and this is the same situation? Give me yes or no. Same or no? Do you see the similarity? You know who this is, no? This is the R group, ethyl group. That means the chlorine must come at position 2 or position 4. So do you notice that this Cl is on the ring? Now, is there any doubt in your mind that it's not just about chloroethane and chlorobenzene? It is about Cl on the side chain and Cl on the ring. Give me on a scale of 0 to 10 how clear you are in what I said just now. It's about Cl on the side chain and Cl on the ring. It's not about chlorobenzene or chloroethane. I need everyone to confirm that. Because I will teach you chlorobenzene and chloroethane. Examination, they will give you something. I'll give you some practice questions, obviously, for it. Okay, I think you're ready. Let me know if I can go to my next page. That's it. I have to just tell you what happens in chloroethane hydrolysis, what happens in chlorobenzene, why there is a difference, and with that, this chapter will finish. I'm waiting for you to tell me if I can go to my next page. So what I was saying is, what was I saying? I am saying chlorine on the ring and chlorine on the side chain are two different things. So chloroethane represents chlorine on the side chain. Chlorobenzene represents chlorine on the ring. So whatever I teach you for chlorine on the side chain and chlorine on the ring, accordingly you will use those comments for the exam questions. Let me give you an example. If you're ready, let me go to the next page. Okay, everyone has copied out everything, what you need to know. So I want to do hydrolysis. Basically, I want to kick out the Cl. Now, you might remember your previous year in your AS level, you could remove the Cl and replace it with OH by using NaOH aqueous hot. Give me yes or no, you remember. You did nucleophilic substitution reaction. This is a primary halogen alkane. You did SN1, SN2 mechanism. You did nucleophilic substitution. You can remove halogen, bring OH. You can remove halogen, bring NH2 using ammonia, correct? Ammonia in alcohol. Or you can remove Cl and bring Cn by using KCN. You have done all of that. Give me yes or no, you remember that. So I'm using one of the nucleophilic substitution reaction. So you notice carefully that if I use NaOH aqueous and if I heat it up, it is possible for me to kick the Cl out and I will get here CH3, CH2OH plus I will get here NaCl. So I understand this reaction was possible. You have done this in AS level. But if I do the same reaction with chlorobenzene, so I'm doing now the same reaction. NaOH aqueous heat. I'm also using heat. We find that there is no reaction happening. Okay, which means ease of hydrolysis. Of course, we have to understand why is it happening. Ease of hydrolysis. In fact, increasing ease of, okay, no need. Only two compounds are there. So ease of hydrolysis means I can hydrolyze chloroethane much better than chlorobenzene. So far, okay. Everybody, give me yes or no. So far, okay, you've seen the difference. Okay, that means Cl on the side chain can be kicked out, but Cl on the ring cannot be kicked out. Everyone agreed? Give me yes. Why for yes? Everyone's okay so far. I will now discuss the reason why this is happening. Let me know if I can go to my next page. Cl on the side chain can be hydrolyzed. Cl on the ring cannot be hydrolyzed. Even with NaOH aqueous hot, not possible. So we have to now very clearly understand. Okay, I'm waiting. I try to move the chat away from the main screen onto my phone so I don't have to. So, ready? Okay. So, reason. This is very important. It has come so many times in the exams. I told you how the questions come. They will slightly change, they'll put some mango tree, papaya tree in the compound, but it will be basically Cl on the ring compared to Cl on the side chain. So let's understand what is happening with C6H5Cl. So when it comes to C6H5Cl, okay, so this diagram gives you a bit more perspective here. I will write the comment. You don't have to draw the diagram in the exam, but this is just a little idea as to what's happening. Now you might remember there is a pi-electron system in benzene ring, correct? Everyone remembers pi-electron system, and you know it keeps on moving around the carbons. And what happens is the chlorines uh, lone pair electrons. The thing is, it gets drawn into the pi electron system. So the chlorine's lone pair of electron is getting into the pi electron system. I will write all the comments first, you understand. So because of this, what happens? The pi electron system, notice carefully, I did not make the inside circle because this is the pi electron system. So the pi electron system, don't forget it has two clouds, no? One on the top, one down, correct? I hope you remember that. So pi electron system, the top cloud and that's the bottom cloud. So it kinds of gets extended on the CCl bond. Now you have done AS level. I'm sure you remember that single bonds are sigma bonds. Double bonds are sigma and pi. So what happens now? The pi electron system gets extended. That's the key word. It gets extended on the CCl bond. So now what is happening? The CCl bond is getting a partial pi character. It's becoming more stronger. And because it becomes more stronger, that's the reason why this CCl bond cannot be broken with inert aqueous heat. Okay, so that's the issue. Let me just write down and I'm waiting for your questions. Give me 2 minutes. Let me write down everything and I'll pick up your questions. So the main thing what you will always mention in the exam, and I insist please learn it exactly the same way. So you just say the lone pair electrons of Cl gets delocalized into the pi electron system, into the pi electron system, or you could say benzene ring. So partial pi bond character spreads over CCl bond, making it very strong or very less reactive. Okay, please copy paste this answer everywhere, anywhere you have an exam situation. This is Cl on the ring. Note carefully, this is for Cl on ring. When I say Cl on the ring, I'm talking of benzene ring, obviously. Okay, let me know when you're done. If you have any questions, now is a good time. Once you're done, I will go to the next page. I will tell you what's happening in chloroethane, Cl on the side chain. Why is that it's able to go? Why is that the Cl can be kicked out in a nucleophilic substitution reaction and we can actually bring the OH or the NH2 or whatever. But we are talking of hydrolysis, so I need to bring the OH. Waiting for your questions. Is your understanding clear on this one? So the lone pair of electron of chlorine got pushed into the pi electron system. So it became like a part of the pi electron system. So the pi cloud is not only on the 6 carbon, it is spreading on the CCl bond. So the CCl bond is becoming like it has sigma bond also and it has a partial pi bond also. That is why the CCl become very strong. So NaOH aqueous cannot break it and it cannot kick the Cl out and push the OH. So you can't change that into phenol. I will be teaching you in the next chapter Topic 32, how to make phenol. Okay, so let me know if you're ready. We are going to the next page. If you have no questions, could you type NQ? NQ means no questions. And let me know if we can go to our last page probably for today. Okay, good. Let me know if everyone has copied out everything. We are now discussing, so what's happening in chloroethane, which is basically representing what's happening on Cl on the side chain. Very, very important. This has come like so many times in the exams. Please make a special note of it and make sure that you learn it very effectively. Comparison questions are very important for paper 4, usually 3-4 marks in the exams. Okay, till now I have only one kid who's told me that everything is okay. Um, okay, great. So all done. So now let's understand. So what's happening in CH3CH2Cl? This represents Cl on side chain. What that means is I can give you something like this. Like I can give you fancy stuff like these. I can give you it in any way. Okay, it doesn't matter what it is. So different kind of situations. So for us, let's focus on chloroethane, obviously. So when it comes to chloroethane, this is also something that you have done in your AS level. Tell me how many of you remember positive inductive effect? Do you remember what it is? Positive inductive effect. Positive inductive effect, the alkyl group, this is not ionization energy, right? So the alkyl group, they have this tendency to push the electrons away from them. They are actually also electron donating group, as we say that. We did know today, ring activators. R is a ring activator. So it also is electron donating. So they push the electrons away from them. And because of this, now let's try to understand, see the situation once again here. So I will explain very quickly and then I'll write down the main comment which you will actually memorize. So this is the situation here. Okay. Uh, no, I added extra carbon. Okay. So what is happening is this R group is pushing the electrons this way. Now, because it does positive inductive effect, now you have to think, okay, so what is the effect on the CCl bond? Your first instinct will tell you what? This CCl bond, what is your first instinct? You will say, oh, the CCl bond should become strong. Agreed or disagreed? Agreed or disagreed? Won't that be your first instinct? Oh, electrons are being pushed into that, so CCl bond actually becomes a bit more stronger. The trick is, it is strong, yes, but that's why we need NaOH aqueous heat. If you use NaOH aqueous cold, the reaction won't happen. You require NaOH aqueous heat. It is strong, CCl is strong, but it is not as strong as the CCl of chlorobenzene. Have you understood the main key points there? So all you have to learn is these are the main points. The positive inductive effect, because later on I will be adding one or two more compounds, so you have to use these words every time. The positive inductive effect caused by the alkyl group. Alkyl group. So any question that comes in the exam, just say alkyl group, all mango tree only. You can say alkyl group, or you can say, oh, the CH3 CH2 group, because we are discussing chlorobenzene, so that is the alkyl group. If I give you some fancy compound, you will say alkyl group, don't say CH3 CH2. Caused by alkyl group makes the CCl bond strong. You still have to say strong, but you have to make a comparison, but not as strong. You understand that there is no pi bond character and all coming. No, that was only in chlorobenzene. There was a pi bond. The whole pi electron ring came onto the CCl. That made CCl very strong. Here, positive inductive effect is happening. Some electrons are being pushed towards the CCl. It is becoming strong, but not as significantly strong. Not as strong as the CCl of chlorobenzene. So this is a nice and easy way to wind up the comparison between chloroethane and chlorobenzene. This question has come so many times in the exam. Please learn it correctly. Okay, this is very, very important for you. Okay, so make sure everything is all learned properly. Good memorizing points there. And the good news, that's the end of this chapter as well. So that's the end of topic 31, which means when I see you next session, we'll be discussing topic 32, which is the hydroxy compound. Phenols, we'll be talking about phenol chemistry, how to make phenol, what are the reactions of phenol. So that'll be another interesting, more reactions, more reaction conditions coming in. Okay, if you have any questions for me, let me know.